sines and cosines that you don't like? Okay. So here's this, we've got this vector function, and that instead of t, which is the, oh, there we go. Instead of t, they're just using u. I mean, t is just the common symbol, but u is fine. So basically, what is our vector function u? Cosine u? Right, they gave it in parametric form. If you want to give it as a vector form, it's this. And then they said, and so what is this about? Cosine 5 pi over 6, sine 5 pi over 6, 5 pi over 6. So it's a point on the curve for very obviously what input value of u? 5 pi over 6. I mean, they're just like handing it to you on a silver platter there. 5 pi over 6. So they gave you the vector, the point that's from the output when the input is 5 pi over 6. So and so if it's going to be the tangent line, you said to write the equation of the line, you need what? You need a point and a direction vector, right? So there's your point. Half done, right? So if it's the tangent line to this curve, then all we have left is the direction vector. First of all, what is this? How would you describe cosine u, sine u, u? So just by looking at that, you should be able to imagine what that is. Cosine u, sine u, u. So we look at cosine u and sine u for x and y, and that's our just unit circle, right? That's just our unit circle. And then as u increases, z increases with it. So can you imagine what that is? You should be able to. Just a spiral going up, right? So what surface does this lie on, the spiral going up? So it's just a spiral heading up like this, or heading down if u decreases, right? And so that lives on a surface, and so the skill you should have is given a curve, a vector function curve that lies on a surface, what surface does it live on or lie on? So what would it be? What surface does it live on? A cylinder. So can you write the equation of that cylinder? So it's a circular or elliptical cylinder? Circular. Circular, right? Circular because you've got same radii in the x and y direction. So what is the equation of that cylinder? What's that? 1 equals x squared plus y squared. So x equals cosine u and y equals sine u. The key fact that gets you from these vector functions to a surface, if it's an ellipse or a circle, based on ellipse or circle, is going to be what? Cosine squared u plus equals 1. So this is your go-between between surfaces and space curves that are based on an ellipse or a circle. That's your go-between. So we're going to take the mathematical equations for x and y, using that to get the equation of the surface, which we know is a single equation of x, y, and z. In this case, x and y. So this one's real easy, right? So cosine squared plus sine squared equals 1. Then, well, here's cosine, here's sine. So that implies that. What? What's that? X squared, and that's y squared. And well, we know that's the circular cylinder. It's based on the unit circle, right? So if you look straight down on the xy plane, you'd be looking at a circle. Let z vary, and you get that whole cylinder. So that spiral lives on this cylinder because the math agrees, right? The math of the spiral is consistent with the math of the cylinder for all xy points xy. Okay, that was for free. You don't have to pay me for that. All right, so now we need to get the equation of the tangent line at 5 pi over 6. So let's just say that's right here. It's not, but I'll just for the drawing's sake. And so there's some tangent line to the, and what do we need to get that? Point. Do we have the point? Yeah, it's the given. That's given. And now we need a direction vector. So how are we going to get the direction vector of this line if the line is tangent to the curve? We're going to use the, remember what we said last time, the derivative always points in the direction of the curve, right? So if we take the derivative and the derivative is a function, right? So the derivative, let's do it in blue. The derivative is the function, what? Negative sine u, cosine u, and 1. Okay? So that's a function, right? That's given any u. It gives us, say, like right here. Where's it going here? So if you take the u that gives you that point and you plug it into the derivative function, it'll give you that vector, right? And the magnitude of that vector is? Or corresponds to? So the direction is the direction of the curve at that moment, right? It's pointing, like if that was a particle flying, it's pointing the direction the particle's flying. And the magnitude of the vector it is? Okay, it's rate of change, right? What rate of change is it? Right, so it's the rate of change of the curve, how much curve is spanned out with respect to how much u changes, right? So given a change in u, how much curve do you get? All right, and that's really the same thing as velocity, speed, right? So the magnitude of that vector is like the speed of that. If that was a particle flying through space and u was time, then the magnitude of that vector would be the speed, and the whole vector would be the velocity. Remember we talked about velocity vectors versus speed being a scalar? So the speed would be the magnitude of that vector, and the velocity would be the whole vector, right? Direction and magnitude. So if we want the direction vector of this line, what will we do? How will we get the direction vector of that line? We're going to plug what into, so the derivative, the vector derivative function, it's going to give us that vector as long as we use it correctly. What do we have to do? Plug in 5 pi over 6, right? So this is the point, this is for the input 5 pi over 6. So we want r prime, that vector, that blue vector I just wrote, is r prime of 5 pi over 6. Okay, and then do I have to find the unit vector for that? Right, all you need is any vector parallel to the line. Any vector. It could be 100 units long, it could be 1/10 of a unit long. It could be 1 unit long, doesn't matter. Doesn't matter what the magnitude when you're using it to create a line, right? Because we saw there's infinite number of points on a line, or on a curve, on a line, sorry, an infinite number of direction vectors, right? Any scalar multiple of any parallel vector will be satisfactory to define the line. So I'm going to use the given point, I'm going to use that direction vector, and then they're asking for the equation of the line parametrically. Okay, questions on this one? So then you're going back to what we learned about the equation of a line, and you're plugging the point in and this direction vector. Are we good? Okay, so we were talking about, yeah. So here's the vector function t. Shoot, I just saw it and I forgot what it was. T2 cosine and sine. And then I'm showing some vectors. I'm showing a blue vector and a black and a red vector. And I want you guys to ascertain what each of those are. So black, so and blue, and red. So both a verbal description and mathematical representation. Can you do both? So yeah, so what is it? What's our name for it? What does it mean? And then also mathematically represent it. Represent it with mathematics. Go. Talk it over, okay? All right, let's see here. Mr. Austin, you pick. Black, blue, or red? Tell me one. You get to pick any one of those three.
Blue.
The blue one. What's the blue one?
So blue is a position vector for that curve.
Okay. He says the position vector for the curve. So if I were to write out a mathematical statement, what would it be to represent the blue vector?
Would it just be what you already have written down? Opposites.
He wants the blue is this thing I've already written down. Correct. Got it. It's RT. I'm not going to write it again, but I will write that, right? So I can just write, or I can just write R, right? Yeah. The blue vector is R of T. Okay, David? Red is the derivative of that. So tell me, what is it?
Like what that thing is?
Anything. Both.
1, -2 sine t.
So you're telling me mathematically what it is? You said 1 and -2 sine t. Okay, and what does that mean? What is that thing? Is it speed? Not quite speed, because speed is a scalar, right? So instead you could say it's a velocity vector, right? If this vector function is modeling something traveling in space, then blue is position. So if it were, so it's not always, okay, but that's a very common application of these, that these vector functions model something flying around in space. And then yes, the blue one is position, and the red one is velocity. And what would speed be? So could you find speed? What would you do? How would you find if I want to model speed in this situation? Yes, sir?
It's the magnitude of r prime.
Okay. Magnitude of r prime. And what is that? Is that going to be a vector function, a scalar function, or just a vector, or just a number? What will you get? Just a number, a scalar. Agree with that? Let's do it. What is r prime of t? So tell me what I would write. Square root of 1 squared plus -2 sine t squared plus. Okay, if you're going to use the shorthand notation for sine and cosine, just make sure you know what you're writing, okay? But it's, especially at the end of the course, we're going to have these long equations with lots of ugly sine and cosines, and this is very helpful, okay? Just make sure you know what you're looking at, and the person who's reading what you're writing knows what they're looking at. But that's fine, as long as you understand. Okay. Yes, please.
It's going to be a function, but once you plug it in at a specific point, it'll give you a scalar.
Okay, so exactly. So then what kind of function is that? Exactly. Scalar function, right? So it's still a function, but now the output is not a vector, it's just a number, right? You're going to plug in a t, say 10, and it's going to spit out not a vector, but the number, the speed of the particle or the thing at t equals 10. So it's a whole function of values, right? And is this a constant? In this case, is it constant or a changing function? How do you know that, Julian?
Well, the vector is changing magnitude. And also,
Right.
If you plug a t, you get a different value.
Right. Okay, so what about now? Is it low or high? Pause it. Yeah, when I said it, it was different than when you said it, right? Okay, so, all right, let's see. So, what about now? And why is it low? What's that? Yeah, so it's close to the unit. But why in this situation is that speed lower? Why is that causing that speed to be lower? Yeah, Harrison. So in this particular function, with more curve, what happens? With more curve, what's happening?
T is changing.
You get So yeah, it's like most of the function is giving most of its energy to turning, right? And so when it does that, for the same change in t, what are we seeing?
Less curve.
Less of the curve is being drawn out, right? So for the same change in t, you have less of the curve drawn out. So that's why that velocity vector is shorter, or the speed would be less. But then coming over here, what about up here? It's faster here because there's less turning. For the same change in t, you get what? You get more of the curve, right? You get more of the curve for the same change in t, so you're going to get a bigger velocity vector and also a bigger speed. Okay, which leaves the black. So what is the black function, or what do you suppose it is? Let's see here. Eric.
I'm guessing it's the acceleration then?
Acceleration. So acceleration is actually, we're going to start talking about acceleration on Monday. Acceleration is a complicated thing because there's two kinds of acceleration. There's acceleration due to speeding up and slowing down, which you're familiar with, or that's most common thought of acceleration. But then there's acceleration just from the fact that something's turning, it's accelerating also. But we'll dive into that more on Monday. So that makes, so let's get into that Monday. But so it's not acceleration because
Wouldn't accelerate x-wise.
yeah. So what is it? That's what we talked about on Friday.
Direction. You get that?
Just the direction of the velocity. Just the direction of the velocity with magnitude 1. So what would it be? It would be the unitized. So now what about this? When you do that, you get what we call the unit tangent vector. And is that a vector function, just a single vector? Is it a scalar function or just a single scalar? What is that when you do that? If you took take our velocity and unitize it, vector function, a single vector, a scalar function, or a single scalar? They're saying vector function over here. Agree with that? Yeah, so this is a function of vectors, right? It's all those black vectors that you're seeing. For different values of t, you get all these different black vectors that you're seeing, and all those vectors have magnitude 1. They're all unit vectors. So it's like if all you care about is the direction of the object flying, you don't care about the speed, then you want the unit tangent vector because it maintains a direction of magnitude of 1, and just shows the same direction as the velocity vector. Okay, questions about that? All that stuff. Yes, please.
Is it about changing the magnitude? Because I thought it was changing the magnitude.
That's just, it's not. Maybe relative to the red one it is, but it's just kind of the perspective on it. So maybe this will help if you look at it like this. So you see the red one is starting over again. So that black one is really maintaining the same. Can you see it? Is that better?
Yeah.
The red one is definitely like growing here and then much smaller here and then much larger here. But that black one is just holding its holding its magnitude of 1. Okay, so the next thing we want to talk about is, let's focus on those tangent vectors. And want to talk about something called the unit, normal, and binormal vectors. So if we have a space curve like this, so imagine that's not just in the plane of the screen of the page, but that's actually going through space, right? That's actually changing in all 3 dimensions, x, y, and z. Okay, so let's talk about, say at this point right here, change it. That'll be easier. Okay, so what did I use for the actual color for the other one, the last one? Was it black? Was it black?
Blue was the RC position.
Blue was the original?
Yeah.
So I'll just be consistent here and stay with that. So that's, say this is R of 3, say, okay? So when your input value is 3, you get this point, or that vector. Okay, and so then if, but then there's also a direction of the curve, right? There's a direction of the curve. So for increasing t, say it's going this way, from left to right, generally from left to right. So if you thought about a clock, if this was the center of a clock, at what time would the r prime of 3 be pointing? What time would r prime of 3 be pointing? What would you say, Matthew?
We're just looking at.
So yeah, so r prime of 3, this is a clock right here like this.
Okay.
Then just about what time, so if you had r prime of 3, about what time would that be pointing at?
So maybe like the minute hand or hour hand would be on the 2, so it'd be on the right.
2, so
Yeah,
r prime of 3 would point this way?
No, not our prime of 3.
Yeah, r prime.
Our prime would point down and to the right.
So like
Yeah.
4 o'clock?
4, yeah.
Right.
The original position would be.
Yeah, so the original position, but r prime
Yeah.
would be, well, at 4 o'clock. Right? Because that's the way it's going. Okay. So then, if we looked at, say we looked at our, and then particularly t of 3 would be what? The unit version of this, right? The unitized version of this. So let's draw that. So I'm going to draw t of 3. There's say t of 3. Okay, so imagine that's a unit vector, and it's the same direction there. Okay, what about t of 3.01? What time would that be pointing in? T of 3.01, Simon, what do you think? What if this is pointing at 4 o'clock? What about t of 3.01?
Just below that.
Yeah, so yeah, right, like 405 or something like this. So it'd be just a little bit lower, right? Because if you increase t a little bit, you see that you're going to be pointing a little bit more steeply down. Okay, so something like this. Agree with that? All right, but now I'm going to put those tail to tail. So I'm going to take t of 3 and t of 3.01, or kind of like t of 3 plus dt. And put those tail to tail. And then I want to look at the difference between those two. So I want to look at the change in t for this change in d, the change in big T for the change in little dt. So what would that vector be? If I want to talk about the change in, or in other words, what is t of 3 plus dt minus t of 3? Tell me about that vector. What vector would that be? So I want a vector that represents the change in this unit tangent for a little change in my independent variable. Paul, can you tell me what that would be?
That'd be a vector going from the tip of t of 3 plus dt to the tip of t of 3.
This way?
Yes.
So the final minus initial, right? So it would be the other, this way. Right there. See that? So I'm going to take that vector, okay? So what am I really talking about here? If I say per unit change in t, then what is this thing representing here? Change in the t vector for the change in independent. What concept is that, idea is that? Please know this. We're in calculus 3. What's that? Rate of change, right? Derivative. Change in y over change in x, right? Change in output over change in input. This is like the derivative. So if I was to take the derivative of the t function, do you see that that's kind of pointing in the direction of what? What direction is that pointing? How you're turning, right? So it's like, are we, at this moment, at 3 seconds or 3 minutes, whatever, are we turning to the left or are we turning right if you're in a car? Aren't we turning right, right? Aren't we turning right? So do you see that that vector, that's like the change in my unit tangent, is showing which way we're turning? And how would that be positioned relative to r prime of 3 then? Like this, right? And then how would those be, what's the relationship of those two then? Orthogonal, right? So this is like essentially orthogonal to that one. So I'm taking, it's like the rate of change of this unit tangent vector. And that the rate of change of that is really a direction, right? So and we're going to normalize that. We're going to take that whole thing and we're going to normalize this. Unitize. If we unitize that, then what we're talking about is like a direction that represents the rate of change of the unit tangent vector. So essentially, mathematically we're doing this. We're going to take the rate of change of t, and we're going to unitize it. And that's going to give us this unit vector that points orthogonal to the derivative and tells us the direction that we're turning. And that's called the unit normal vector. Sorry, I don't have a fancy slide for you. I'll make that for next semester. Yeah.
Sorry, so it tells you which way you're turning?
It tells you which way you're turning. Do you see that right now at 3 seconds or 3 minutes that if you're driving in a car along this thing, you'd be turning right, right? Do you see that? Because you're coming around this curve here like this. So if you're in that car and you're coming this way, you're turning right. Well, that's telling you you're turning right. So it's orthogonal to the direction you're going, showing you which way you're turning, and has length of 1. Alex?
So wait, is that r prime t?
Not quite. It's yeah, kind of. But then just considering the direction. Just the direction.
Okay.
So it's because right, r prime is like acceleration. So this is the direction of acceleration just due to turning. So it's part of r prime. It's actually just it's part of it, not all of it. Does that answer? And so when we really dissect acceleration, I think it'll make more sense. Okay. All right, and so then there's a third vector called the binormal vector, and that is, sorry, so I drew r prime of 3 there. I want to just change that to t of 3. Is that okay? So now we're just looking at the unit vector in the direction of motion. So that's what that is. The unit vector in the direction of motion. And then this one is n of 3. That's the unit vector describing how the direction of turning. So turning to the right, in this case, turning to the right. So it's going to go out perpendicular to the direction of motion, turning to the right. All right, so then the last one is what's called the binormal vectors. So the binormal vector is t cross n. So that's usually capital P. So talk to the person next to you. Explain what that would be like. So what would that vector be like? Direction and magnitude, right? Direction and magnitude. If you do t, what we learned about t, cross n, what we learned about n, you're going to get a vector b. So I want you to talk about the direction and magnitude of that vector. Go.
Yeah. Okay. No. Yeah.
Okay, let's regroup here. Rebecca and Julia, what did you guys talk about? Rebecca.
Because the vector t and vector n are already orthogonal to each other.
Okay.
The magnitude of vector b would be, like, it's a max magnitude basically, so it'd be the magnitude of t times the magnitude of n.
Okay, so since they're orthogonal, the magnitude of that is going to be the product of the magnitudes, which is what? What is that? Did you say what? Or yeah. What is that product of those magnitudes? What is the magnitude of t? What's the magnitude of n? These are all unit vectors. These are all unit vectors, right? T was the derivative unitized, right? T is the derivative unitized. N is the unit tangent, the derivative of the unit tangent, unitized. So they're both 1. So therefore, P of t, magnitude is 1. Okay, what about direction? What about direction?
I mean, it's orthogonal to both of those.
Right? Tell me, be more specific. So, Junsi, what'd you say? What about the magnitude, or the direction of B of t? Coming out at us. Is it coming out at us? Out of the screen? Put your fingers, your right hand fingers in the direction of t so that they curl towards n. Put your right hand fingers in the direction of t so that they curl towards n. You should find it's going into the page. Right hand. So I'm going to point. So I'm going to point my fingers in the direction of t. So that's like this. So now how do I orient my hands so that they curl towards n, this way. You see it? So you should have said into the board. So that would be B of 3, okay? So now it looks like this. Does that look like it's going back into the board? Kind of? Yeah, okay. All right, so what you have then with the T, N, and B vectors is you have this like little, it's like three-dimensional space, right? T and N and B are all orthogonal to each other. So it's like a little R3 space that moves along the curve, right? So it's this like little, it's like this R3 space that moves along the curve. And what is T? What's the direction of T as you're moving along the curve? T is also always. So if we're a point, okay? So here we are, we're a point. So you're the point. What does T mean for you? The point. Direction you're going. Okay? What does N mean for you? Direction you're turning, right? It's the direction you're turning. What does B mean for you? Who knows, right? It's so. But one thing we can say is like T and N. All right, T and N form a plane. Okay, and that plane is what? What plane? How would you describe that plane that T and N form? If you're the point, you're a car moving on this road, right? In space, a spaceship in space. Okay. The plane formed by N and T is like the plane, the spaceship, what?
When you're currently moving on.
Yeah, you're in, right, exactly. It's like the plane that you're in. And so B would define that plane because it's orthogonal, right? We need an orthogonal vector to define a plane. So B defines the plane that you're in at any given moment. All right, so let's summarize. So really, with these three vectors and this three space, we also have three planes. We have the plane of N and T, we just talked about. We have the plane of B and T, and the plane of B and N. So maybe the plane of B and N is the easiest one. What is the plane of B and N relative to your motion? The plane of B and N relative to your motion is what plane is that?
2T.
What's that?
It is defined by T.
It's defined by T, but like what is it relative to your motion? The plane of B and N. Yeah, it's like the plane that you're directly going perpendicular through. Do you see that at the moment? So that's called the normal plane. Okay, so the normal plane is the plane that contains B and N and is defined by what? What vector is the normal plane defined by? T. Notice that. The normal plane, the orthogonal plane to your motion, is not defined by N, the normal vector. It's defined by T, the unit tangent vector. Hear me now. Hear me well. Learn it. Okay? What about the plane of T and B? Oh, what kind of plane is that? That's the tangent plane to your motion, right? So you're coming, it's the tangent plane to your motion. So that's the tangent plane, the plane of B and T. And notice, what vector defines the tangent plane? If you were to write its equation, you would need what vector? N. N is the orthogonal vector to the tangent plane. So you use N to write the equation of the tangent plane. So can we quickly go through this? So just, you can look at this on the, I thought I had this revealing, but I guess not. Okay, so we've got three planes. So we said the normal plane, don't try to write this down because you guys want to leave. All right, so the normal plane, just look in the video or we'll go over again Monday. The normal plane is orthogonal to the curve. It's like the curve is piercing through orthogonal to that, right? But you're not going to use the normal plane to define that vector. You're going to use the tangent plane because the tangent vector is orthogonal to the normal plane of the curve. The tangent plane is, right, it's this plane like this. So what vector defines that one? The normal vector defines that one, right? If you were going to write its equation. The last one was the first one we talked about. The plane that the curve is in at that moment That's called the osculating plane, not oscillating. It's not moving. It's moving when t changes, but for a given t, it's not moving. It's not oscillating. It's osculating, and so that's the plane the curve is in. Use the vector b, like we talked. That was the first one we talked about. Okay, so you really have to study these pictures and just keep going over this and thinking about it. So it all makes sense. Okay, I will post the written homework today.